All right, are we ready to go? Welcome back. Good morning. So at the end of the day yesterday, we wrote a little test program using Compiler Explorer. I'll start with just a quick review of where we are so far. So I don't remember where we began yesterday, but let's start somewhere around here. We were working with our calculator circuits. So we pipelined the calculator, stretched it out over 2 cycles, and then we added the memory to it. Well, we applied valid and learned about the concept of validity and clock gating. And then we added the memory to our calculator, which, as I said, is probably the most difficult lab of the whole course. So you got through that one. I think you'll be okay for the rest. If you have time, so I jumped over programming the FPGA because we had done that with the earlier version of the calculator. Same behavior on the, that you can observe with the FPGA board. But hopefully I've fixed the issue with the debouncing. So if you have time during one of the labs and you race ahead and you want to try out the FPGA board with your calculator, hopefully you've still got your calculator circuit handy. Feel free to try that out. I guess. So I need you also to patch it to get the fix for the debouncing. Maybe I should just go ahead and show that fix. So the course repo, GitHub, if you don't have it up, go ahead and open this as well. GitHub.com, Steve Hoover / GIAN course. So the reference, not the reference solution. I guess it's the shell. Actually, let me just look at the commits. No. Let me think. So the repositories that we copied. So you've got a copy of TTGIAN and why does that not have commits? All right, well, we'll get back to that. If you want to try it out with the debouncing. Oh, you're right. Okay, that's what it is. Oh, so I think I changed my clones instead of changing the baseline. So I'm going to have to fix this as well. But let's see if that's where I did the change. Oh, I don't think that's it either. No? Okay, well, I'll have to figure that one out for you. But anyway, back to the course content. So we've been talking about assembly and disassembly and going through some exercises for for the definition of the RISC-V instruction set architecture and how to use that to assemble and disassemble instructions. So I'll just go to this all-inclusive ugly slide, right? This defines the instruction format and the fields of the instruction based on the instruction type, which you can get from the opcode. This table is breaking it down to individual instructions based on the opcode field, the func3 field. And so we can use these tables to assemble and disassemble. I think, so do you still have all the materials at the tables? Or did we collect those? So hopefully you've still got all your RISC-V cards. We'll do some more exercises as we go. All right, so today we'll start here. I pulled up the RISC-V green card before, and we saw this, but just to review, the register file has 32 registers, -1 because X0 is a hard-coded 0 value, and there are conventions for the usage of these registers. Mostly it's around calling conventions for, one function to call another function. How does it pass values to that function? So, so those calling conventions are illustrated here. This is generic, not specific to RISC-V, but it's the same in most instruction set architectures. So there's a program is going to, one function is going to call another function, is going to call another function, is going to call another function. Those functions will return, and when they return, they need to return to the context that they called from, right? That context includes all the local variables of the function. And so to support that stack of function calls, there's a stack in memory to hold on to all these variable values. The stack, for some reason, conventionally always seems to grow upward, so you're subtracting as you grow. The top being addresses towards 0. So here's depicted a function draw square. Draw square is going to draw a line. So draw square's context is in blue here. It's referred to as a stack frame. So the stack frame includes draw square's local variables. It includes a return address. Where is it going to return to when it finishes? And it includes the parameters of draw square. Then draw square calls draw line. We establish a new stack frame for draw line, which has its own parameters passed from draw square, its own return address, which would return to the draw square function at the point of the call, and its own local variables. Okay. So in Compiler Explorer, when you compile your code, if your code has say a main function that calls the function that you write, you're going to see a lot of instructions that are just managing this call stack and managing the local variables. It can be very confusing to look at all those instructions, so I'm going to walk through an example just to give general context, to hopefully give you enough sense of what's going on that when you're looking at this code and stepping through it, you can eventually decipher what's going on. And of course, it's going to be different depending on the optimization level, depending on the compiler, but the conventions that are necessary for one function to call another function need to be consistent in case they're compiled by different compilers, for example. So here we're looking at main, which calls a square function. And this is code that I generated with Compiler Explorer and tried to reverse engineer myself to figure out what was going on. I may get some of the details wrong, but hopefully I get the general sense. So main generated this load immediate. It's loading a value of 6 into A0, right? That's the parameter. So A0 is used to pass the parameter from the caller to the callee. This is kind of a shortcut to pass it in a register, right? If you use low level of optimizations, all of this parameter passing is all through the stack in memory, okay? Yeah, A0 is a register, right? That's looking up here, A0 is register X10. So the registers named A are function arguments. ABI, Application Binary Interface, and don't ask me why it's called that, but that's what it stands for. Yeah, it just makes it more readable. You know, uh, I can tell that the SP register is the stack pointer. I don't have to decipher X whatever. So, so we call square, and then in square itself, square is going to set up its stack frame. So the stack frame for main is referenced by S0 being the base of the stack frame and SP being the pointer to the top of the stack frame, top being the lower memory address. To establish the new frame, S0 is going to become main's SP, and then we'll establish a new SP for square. Yeah, so I'm going to step through each of these instructions. So to establish that stack frame, right, the first thing we do is subtract 16 from the stack pointer. That takes us from this stack pointer to this stack pointer. Then we do, let's see, store. So this is capturing the parameter 6 in the stack frame for square. Essentially, it's establishing that 6 as a local variable in the stack frame. This is not highly optimized code. I think the way this is written, there's no need to actually store RA. If there were a function call in square calling another function, right, you would have to have RA captured in memory before the other function would be able to use that register. So then we're updating actually we're storing the old S0. So this, the mains S0, so that when we return, we can restore mains stack frame, right? So we're capturing that stack frame pointer. That wasn't actually illustrated here, but that's also needed to be able to restore the state when we return. Here we're updating S0, so it seems kind of weird that the compiler chose this order. You would think it would update the whole stack frame together. I guess it needed to keep S0 so it could save it off. But anyway, here we're updating S0 to reflect square's stack frame. We could subtract 16 from it. For whatever reason, the compiler chose to do it as an offset from stack pointer. And then storing the, actually, what are we doing here? Oh, okay, here we stored S0. I thought we had already done A0. So this is storing off A0, which is a local variable. I think I misspoke earlier. And then, for no apparent reason, loading it right back in, right? Which of course does absolutely nothing at all. We're storing A0 into this address, and then we're loading into A0 from the same address. Again, this is optimization level 0. So sort of at this optimization level, all the locals are in memory. When you need access to the local, you load it from memory first. With any level of optimizations, that's going to disappear. And then the actual function of our square function, right? We multiply A0 and A0. And then we return. So we have to reestablish the caller's stack frame. So let's see, RA, the return address. So we need to, actually, why do we do this? Oh, okay. So when we called the square function, this call instruction is actually a pseudo instruction. It's a jump. Think specifically jump and link register. The behavior of that is to, do the jump, meaning update the PC appropriately. Also capture the return address, which would be the instruction at the PC after the call. I can't remember if it's the call itself or the instruction after. I think it's the instruction after. So that was captured implicitly by this pseudo operation in the RA register. Okay, so I think I misspoke earlier thinking that RA was my local. RA was actually that return address. That's what we captured here. And then after doing them all and setting up the return, we need to access that return address, and then we'll use that in the return. So again, return is a pseudo op. It's implicitly using the RA register. So yeah, we're loading RA so that we can return to it later. We haven't actually, again, this is unoptimized code. We don't need this load. RA is already set up. But if this function were to call other functions, that register would be used for other purposes, and we would need the load. And then we're reestablishing the stack pointer, which again, we wouldn't actually have to load, but we're loading it from memory. And so that's reestablishing this S0. And then we reestablish the stack pointer by incrementing by 16, and then return, right? So the vast majority of instructions here is all about maintaining that stack. The actual function in this case is just one instruction. Any questions about all that? Yeah. Which one? This is memory. So it's, in terms of the instruction set architecture, it's memory. Memory is addressable. It holds bits. How we implement that memory in hardware is another question, right? So as far as the model goes for the instruction set architecture, it's just a memory address. It holds 32 bits if we're accessing it using 32-bit instructions, access instructions. The real hardware is likely to have a very complex, hierarchy of caching and whatnot. So ultimately, all of this is backed up by memory, by RAM. It's actually then below the RAM, backed up by disk. And then above the RAM, there'll be various levels of other RAM and, well, I guess it would mostly be RAM, structures for caching to keep the data local to the CPU. I'm not really planning on focusing on the whole cache hierarchy. We're going to do a CPU that just has a very simple toy, small memory, single structure. But that's a whole, I mean, the cache hierarchy for a general purpose processor is much more complex than the CPU itself that we're going to, well, at least the CPU that we're going to design. Sorry, I didn't catch all of that. Oh, this arrow here? This arrow is representing the actual call, right? So when we do the call, we're updating the PC to point to the beginning of this. The arrow is representing the update to the program counter. In this case, we're starting with main, and then we do the call. That takes us up to the square function. Yeah. Of S0 and SP? That's a good question. Let's see, why do we need S0? We're doing everything relative to the stack pointer. I don't know. That's a good question. You got me. Any other questions I can't answer? All right. Yeah, I mean the compiler is restoring SP relative to the other SP, and it's kind of a fixed value for every function what the offset is. So I can understand where the question is coming from. Seems like you know everything you need to know without S0. Not sure. Yeah, I mean it seems to me each one should restore the other as long as this, we can see this function doesn't need S0. Oh, no, here it is. Okay, so these are stored relative to S0, but I'm not sure why they couldn't be relative to the stack pointer. I don't know. Okay, so you've created your test program, right? If you're interested in kind of exploring it, maybe I'll just give you a few minutes to explore your test program with different compiler options, different optimization levels, relate the discussion that we had in this slide with the code that you see generated. So just taking some time to play around. And then we'll take the code that you generate and move that over to Warp 5 and see it executing. Right? So I'll just walk around and try to decipher what the compiler does with you. All right, so many of you are racing ahead already anyway. So what are some of the things you observed playing around with the compiler, with your summation program, or even with the square program? Anybody find anything interesting that the compiler was doing? Well, I know you did. I was talking to you. What are some of the interesting things you found? Yeah, so what were some of the various differences at different optimization levels? Anybody? Yeah, so depending on your optimization level and depending on what your function is doing, sometimes the compiler figures out the result of your function for you instead of executing your function. So the summation program, if you're calling it with a value of 10, the sum is going to be 55. So the compiler will just figure that out, say, okay, we need 55, and assign a 55 instead of calling your function. So the compiler can do some pretty smart things if we let it. Instead of calling the function, it just loads a value of 55. Yeah. Right. Any other observations? All right, so let's look at running the code that we can generate in Warp5. So if you haven't already, go ahead and open warp5.org. And we'll keep things simple, so you can configure your core to be a single cycle pipeline. And in the Program tab, you want to choose Enable Custom Program. I'm not going to do this. I didn't open up Compiler Explorer. Oh, maybe I still. Let me open it up and see. God, bolts. Yeah, that one's not going to work. So for your summation program, right, just cut and paste all the assembly code. I'll do this with my square program, but it's not going to actually work. The square program uses multiply, which we're building a core that does not support the multiply instruction. But in any case, do a custom program, select this, paste your program here. You should see your program appear here, and I don't actually see that. I think this is a bug with warp5.org. Just click this and yeah, basically you need something else to trigger recompile that's not getting triggered by the fact that we just pasted code. So once I've checked and unchecked, or unchecked and checked, this should regenerate. Now I've got my code, and then you can, and I'm going to actually undo that just so I have code that works. So then you can edit in MakerChip as source. This one also works. Take your pick. Then cross your fingers. And once that compiles and simulates, you can see the execution of your code in the visualization. So hopefully if I let this play, it should start executing. The default program is basically the same summation program. So this should execute fine. So this should be doing a summation. It's in the inner loop now, right? These first several instructions were initialization, and now it's iterating. And I can see my, let's see, as it see. I think this one is my loop count. And this one is my summation. Okay, now, there are various things that could go wrong here, right? So when you cut and paste your code from Compiler Explorer and drop it in, Makerchip and the Warp-V core that's generated is not running a whole full-blown OS or understanding the structure of your code. It doesn't understand the main entry point, for example. The Warp-V core that you built is simply starting execution at address 0. So whatever happens to be there. So depending how you wrote your code, very likely that's the top of your function. So the function call has not been set up, right? So the function call should set up the A0 register with the value that you want to, the parameter. So you might have to manually modify your code to, for example, set up execution by doing a load immediate instruction of A0 with your input parameter value, whatever that may be, just to execute properly. A few notes about dropping the code in context, right? You want to keep this structure where your code is inside this assembled statement. Keep it indented underneath, and the indentation of your assembly code, the assembly syntax is also sort of sensitive to indentation. The first label, your code should start out with a label. In this context, that's going to establish the indentation of your code. The labels are unindented, so you want to start out with a label to establish sort of the unindented level here, and then your instructions consistently indented under that. So make sure you have that structure, and I'll walk around and help with issues. But hopefully you can see your code actually iterating over the loop, summing values, and producing the right result. Okay, so now that you've played around with my CPU, let's have you build one of your own. So we're going to jump into the portion of the workshop that's all about creating your own RISC-V core. You'll create a core that's very similar to what you built. So here's a typical block diagram for a CPU, right? Hopefully at this point this diagram makes some sense to you. We have our program counter logic, updating the program counter, generally incrementing by 1, unless we have a branch instruction, which would provide a different branch target or a jump target. Jump target would be the current PC with an offset that comes from the immediate of the instruction. So it's coming out of the decode logic that's interpreting the instruction bits. So aside from branches, the typical flow of the instruction is to fetch the instruction at the current PC from the instruction memory, decode that instruction to figure out what's going on. That's going to provide 2 source register indices, up to 2. Those will be accessed from the register file to look up the values for those registers. Those are sent to the arithmetic logic unit to perform whatever calculation the instruction is requesting, and then write the result back to the register file. Load instructions are going to access data from memory. So the address for the load instruction, similar to this calculation, is an immediate offset relative to a register value. So that is sent off to memory for load or store. Loads will return data, and that data needs to be written into the register file. Okay, so very high-level block diagram of what the CPU does. So first is to set up, to start all this. So we have a starting template again. So you can open up the course repository. And starting point code for the CPU. Right-click, open a new tab. So while that loads, might be a little slow with everybody loading at the same time. Our plan of attack is basically to walk through as the instruction walks through and implement the logic in that order. So we'll start out by implementing the program counter, then we'll instantiate an instruction memory. Instruction comes back and needs to be decoded, so we'll implement the decode logic, we'll implement the register file read, we'll implement the arithmetic logic unit and register file write functionality. And then we'll implement branch behavior. Sometime way later, we'll add a data memory. So let's just wait for everybody's to load. Okay, finally it loaded. So just walking through the template that we have, again, this looks very similar to what you had for the calculator circuit. The main difference here is a couple configuration parameters for the size of array structures. And the main difference is the fact that we've got your program here. So the program that's loaded in by default for the instruction memory is very similar to the one that you were playing with. This is written by hand as opposed to being generated by a compiler, but it's doing basically the same thing, this summation. It's set up, I think I had you sum including 10. Someone was just pointing out to me this one sums up to 9, not including 10. So again, your code goes here, and the rest looks pretty similar. Okay. Anybody still waiting for the code to load? All right, we'll give it another minute. Yeah, and it doesn't have full scaling support yet, so we're hammering on it pretty hard by all loading at once. Maybe just one of you at a time can try a reload. It might be hung for one reason or another. So while we're waiting for that, I will introduce the next lab. So this lab is about the program counter. We're going to create the program counter initially just as an incrementer. We're not going to worry about branch behavior, so the program counter is just a counter. We want to set this up so the first instruction that it executes is instruction 0. That means we want our first valid instruction to have PC of 0. And then after that, we want to increment by 1 instruction. Now, the program counter is a byte address. Instructions are 32 bits, 4 bytes, which means incrementing to the next instruction is incrementing by 4. So this logic is going to operate on a 32-bit address and increment every cycle by 4. So to get those two things right, we need to make sure that that we're starting with 0, not with 4. To do that correctly, we want to reset the PC to 0 if not if this instruction was a reset instruction. So remember, this is set up with a reset pipe signal, right, to, as we talked about before, sort of consistently reset throughout the pipeline. So we can view the instructions as either reset instructions that are clearing things out or non-reset instructions. So when we first deassert the reset, we're going to get the first non-reset instruction going through our pipeline. That one needs a 0. So if our reset logic says 0 on reset, previous value plus 4 on not reset, it's going to end up starting us with a value of 4. We're going to miss that first instruction. So to make sure we're getting that first instruction with an address of 0, we want to apply reset if the previous instruction was a reset instruction. Right? That way we get the first instruction has a previous instruction that was reset. We have that valid instruction that has a PC of 0, and then we continue incrementing. Increment by 4. So otherwise, this is an incrementer as we looked at before. So try to remember. Look back at the previous slides if you need to, when we implemented the incrementer way back when. So the incrementer, right, is this picture. It's resetting to 0, again, resetting based on the previous reset, and thereafter incrementing by 4, so updating the PC to the previous PC plus 4. We're going to do it slightly differently than we did before. When we did this before, the increment function was prior to the mux associated with stage 0. We're going to want an incremented PC value for other logic that we implement. So I'm going to ask you to implement the incremented PC in stage 1 this way to match this diagram, but same concept. Just the PC logic. I don't know if I had a separate slide. No, it's just that one. Okay, so it's just this PC logic here. So see if you can do that, and I'll walk through it after you have a chance to try. After you implement it, you can use the visualization to see if the program counter is, properly incrementing. You can also look at the waveform to make sure the waveform is behaving as you expect. You should really add 4. So the PC is going to be a 32-bit PC, and you want to add 4 to that because it's bytes. Yeah. Right. 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 So the observation is that generally when you structure logic like the PC, the PC mux, which has multiple cases, when you're coding in Verilog, you generally use sequential constructs for something like that, where you would assign a PC by default to be +1, and then you'd have an if condition. If this is a branch instruction, then let's assign it to something different. TL-Verilog, to enable the other forms of abstraction that are valuable for hardware, uses this single assignment model. So your assignment of the PC here is a complete assignment of the PC. We don't have the sequential semantics where we can assign it and then, oops, let's reassign it to something else. It's more declarative of the hardware. And that's why, for things like muxes, we use the ternary expression. It's all in one expression to completely express all the different cases that we might have. It's about the the greater than 1, ahead by 1. Try coding the, what you want for the logic. Try coding the counter, see it simulate, see if it's behaving correctly, and maybe that statement will make more sense at that point, but struggle through it. But we're going to take a break for tea for 15 minutes. And then I'll walk through the solution. So let me talk through this lab solution. My code here. Okay, so implementing this picture, in stage 0, I have my PC mux. My PC mux is going to assign the PC, which is a 31-bit to 32-bit, rather. And that's going to be a ternary expression. It's a mux. So let me start out this way. I'm going to reset. If reset, that's not right. If reset, then I want a value of 0. So let's be explicit, 32-bit 0. Otherwise, I'm going to increment. Huh? Either one. Doesn't matter which base. 0, 0. If it's not reset, then I have my default behavior of incrementing. So according to this diagram, that's going to be the incremented PC of the previous instruction. Right, so the previous instruction computes, this is my incremented PC, the next instruction uses that as the PC. Now I need to assign the incremented PC. So also 32 bits. So my incremented PC is my PC plus a 32-bit, let's call it binary 100. Now, compile this and look at the waveform. Let's hide that. So here's my CPU, my PC, incremented PC, and so here's my reset as a stage 0 signal. And here's my PC, also a stage 0 signal. So these timing match up. And the first instruction that I have that's not a reset instruction has a PC of 4. I want it to have a PC of 0, right? So my logic's not quite right yet. So instead of saying use a value of 0 for reset cases, I want to say use a value of 0 if the previous instruction was a reset. So the first non-reset instruction has a previous instruction that was a reset instruction. So I'm forcing the 0 for that instruction as well. So with that change, I'll get a PC, again, stage 0, of 0 for my first non-reset instruction. This is the behavior I want for the PC. Right? Okay, so I'll just give you a second to make any corrections and absorb that. Not with the same signal name, but you could have another signal that's doing the same function in a different stage. So just making sure everybody is on the same page. Okay. All right, so we have, I showed the reference solutions before. Let me open those again. So the reference solutions here serve as reference solutions for both the calculator and for the CPU. I'm going to open that. So this is just a view of where we're headed with the CPU. If I configure the reference solution for the final CPU lab, which happens to be called TB for test bench. Again, just to give a view of where we're headed here. This is the visualization that we have for the CPU. I probably should have looked at that also with this change. So we have no visualization yet, but soon we'll enable it. So this is the final, the final CPU lab that you'll do. And you see visualization that looks similar to what we had with Warp 5. It's a little more simplistic. And if we play it out, again, this is the program that's doing some numbers from 1 to 9. So if you play it out, you see the PC incrementing, you see the decode, you see the register values getting accessed. We don't have the animation in this one, but the parenthetical here on the numbers is representing the previous value in addition to the updated value. Okay, so just to see where we're headed and also how to use the reference solution if for some reason you need to rely on them. But again, the intent of the reference solution is desperation. I don't want you using it as a crutch. Probably you don't need to use it at all. But especially, for example, after the course, if you want to look back at something and remember what we covered in the course, it's here for you to lean on. All right, so back to the slides. Next is the instruction memory. So the template is providing the instruction memory for you. We're just going to do the hookup. Components like this, the instruction memory, the register file, these are array structures. They're regular. You get them from a library and you instantiate them. I've just built it into the template for you. So, so the first lab is simply to find this statement in the code and uncomment it, which I'll do together with you. And I guess part of the lab as well is not just to make the change, but also look at the log file after making that change. So where did it go? I guess it's way at the bottom. Oh, I'm in the wrong file. Okay, so down here, the IMEM, we want to instantiate the IMEM, so comment that out and compile. And look at the log. So essentially what we did by uncommenting was create this picture. We instantiated the instruction memory. It's not connected up. The instantiation of the instruction memory, in this case, we're not using modules. We're just dropping code in place. That code happens to have signals for the interface of the instruction memory. And you can see all the warnings in the log about these signals that are disconnected. So as we hook up the instruction memory, all these warnings should start to disappear. So it's probably more meaningful to look at the TL-Verilog first and then see the Verilog. So typically in Verilog, you would just instantiate a module. Like I said, in this case, we're dropping down the actual logic of the memory. I haven't introduced all the concepts that are necessary for a memory yet, so the code is not going to mean much to you, but just so you can see kind of how the code is structured through the macro instantiation in this case. I can scroll down to, so here's the instantiation. So this line is telling us that we have instantiated a component from the RISC-V shell lib. This component is the instruction memory. This is the logic of the instruction memory. Again, I haven't introduced all these concepts. I'm not going to explain what this logic is doing. But you can see the warning messages that we have signals that it's assigning that we haven't hooked up yet. So you can, again, as we hook it up, these will disappear. Is that good enough at this point, or okay? So back to the slides. The way we want to hook this up, so this is I don't know why I say prog. Well, okay, it's the instruction memory that contains our program. So this is what that instantiation is providing. It's this IMEM read address, and it has this bit range, right? So the instruction memory is going to get built to be sized sufficiently to hold whatever program we provide. In this case, I believe our program is 8 instructions, if I remember correctly. So the bit range of the address needs to index, the array is going to be 8 entries. We need to be able to index into those entries. So in this case, the bit range for the read address is going to be 0 to 2. We're instantiating a memory that is 32 bits wide. Okay. In reality, RISC-V is using byte addresses, so this would have to be a byte memory. We're making a little simplification here for the course. We're not worried about the byte support for the instruction memory nor for the data memory. So we're only supporting the 32-bit operations just to keep things simple. So we just have 8 entries that are 32 bits wide. We have the address that we're going to read from and the read enable saying yes we want to read or no we don't, and we have the data coming out. All right, so that's our interface. That's what we need to hook up. We have our PC logic that's providing the PC, right? So the address that we want to read is given by the PC. The PC is a byte address, so the lower 2 bits of that byte address had better be 0. We're just going to assume they are and ignore them, and we'll connect up the instruction memory so that the read address is hooked up to the program counter bits down to 2. Okay, and as I said, the instruction memory is going to be sized appropriately for the program, so we need to parameterize its size. We have this constant, which is referred to as M5 underscore IMEM index count, that's going to tell us how many bits we need to index into the structure. So we're going to use that parameter to hook up the program counter, right? So that our code is properly parameterized if the size of the instruction memory changes. Okay, so we're going to hook up this IMEM read address to the PC, ignoring the lower 2 bits of the PC. Okay, so these ranges are the same, shifted by 2, right? This is the index -1, this is the index +1. That's the extra 2 bits. We want this to be enabled always, so we're just going to hook up the enable to always be 1. And hook up means assignment. So again, this is just logic dropped in place. So these signals exist, but they're not assigned or not consumed. The data coming out, that's the instruction itself. Let's give that a more meaningful name in context, right? To the array, it's just data. To the CPU, it's an instruction. So let's call it an instruction. So assign this instruction signal just to equal this signal. And check in simulation that you're actually getting meaningful data in the instruction, right? We should have the program counter incrementing through these instructions, fetching them now one by one, and presenting us with the instruction. So hooking up each of these three signals. And after you do that, you can also uncomment the visualization and see that the instruction memory is fetching. The visualization at this point should have enough to actually function properly, so you can uncomment. It's a default. Yeah, the program is already populated in the instruction memory. Any questions about it? Okay, so go ahead. there was some remaining confusion about the ignoring the 2 bits, the byte-oriented addressing, right? In terms of the PC, right, the PC should be, the PC is a byte address. So when the PC is referencing a particular instruction, it's referencing it by this address. The first instruction, it would be referencing address 0. The second instruction, it would be referencing with address 4, etc. If the PC for some reason is misaligned, so we try to access address 5, we should get a misalignment error. The CPU should go nuts. So the PC should always be aligned to 4 bytes. The instruction memory, the structure itself, it's just an array. It's a standard component. We're implementing it using a 32-bit wide memory. So the indexing for the array structure is 0, 1, 2, 3. So when you have a program counter of 4, that should be indexing into 1. The lower 2 bits of the PC should always be 0. So we're just ignoring them, right? The IMEM is a memory. It's done for you by that macro, right? So the first step here, uncommenting or where is it? The last lab, where we uncommented the IMEM macro, that's instantiating the instruction memory, right? It's giving you this picture here. So at this point, we just need to hook everything up, right? When we instantiate it, we've got this picture with the disconnects. The IMEM macro itself is constructed to hard code the program that we're providing, right? So our template, the template that we're starting with has the program. This program is getting assembled and hard coded into this instruction memory for you. You don't have to worry about any of that. You just need to worry about hooking it up to read the data. Good. So I'll walk through this one. This is sometimes one of those labs that's harder to explain than to actually do. So since the hookup is drawn here from the PC to my memory in stage 0, I'm going to keep the PC logic together, so both stage 0 and 1, and put the IMEM logic together, which means I'm going to take myself back to stage 0 here and do the PC hookup to the address. So I want to hook this up to IMEM read address, which is indexed by this long expression. IMEM index count -1 down to 0. And I want to connect that up to the PC with the proper bit range. So the bit range needs to be shifted because of the difference between byte and words. So this is IMEM index count +1 instead of -1, and down to 2. So that makes this connection here. And I also want to hook up the enable. So that would be IMEM read enable, which is 1 bit, is equal to not reset. So as long as, you know, for every instruction that's not a reset instruction, we want to do a read. And then I can hook up the other side, the output coming out. That's going to drive into a new signal called instruction, which is 32 bits. And that's going to come from IMEM read data. Okay. So should be able to compile that. Make sure I have no errors. Looks good. Let's check the log just to be certain. So I do have a warning. Instruction is assigned but never used. That's expected, right? That's my instruction. All the other warnings for these dangling IMEM interface signals have been cleaned up. This is what I expect at this point. The next step in the lab is to disable or enable the visualization. So I go down here and enable that. And now I can see my CPU visualization. By step, see that the pointer is resetting. After reset, we start stepping. Looks good. Any questions? Mm-hmm. So the ranges here, is that what you're asking about, is the ranges? So again, this is, you know, the difference between this range and this range times 4, right? It's the byte versus word. And we're just hooking up the program counter to the address of the memory to fetch the instruction. Got it? Okay. And you know, the other aspect of this is that it's parameterized. Yeah. Yeah, where does this definition come from? To be honest, it's hard to see. It's buried in a library. And once you go through the macro preprocessor, it's been processed. It's not visible. So, in all honesty, it is rather hidden. You would have to actually sort of chase down the library to actually find it. So we've got these two library includes, the first for tiny tape out, the second for the RISC-V shell. You'd have to open up this code and look through it. You can, I'm not teaching the macro preprocessor, but you could also, after you include this, if you know what name to look for, you can print what's the value of this. Any other questions? It's a read-only memory. Yeah. So after the instruction memory, we've got the instruction. We need to figure out what it is. So we're going to look at decode. This is the bulk of the sort of reflection of the instruction set architecture, is interpreting the instructions. So we're going to do several labs related to instruction decode. So we've already played around with this, decode quite a bit. Now we need to codify what we've already learned. So the first step to instruction decode is figuring out the instruction type. We need to know that to understand how the instruction is formatted, what its fields are. So let's start with the table that helps us decode the instruction type. So the types that we care about for our CPU, right, we're implementing the base instruction set for RISC-V, RV32I. The black type letters here are part of that base instruction set. The ones in gray are not. We don't need to worry about decoding those. And so, I'll first start you out with some of the decode, right? So we're going to make a signal for each instruction type saying, is this instruction whatever type? So I'll do is I instruction. That should assert if this instruction is I type. And I'll start you off decoding these three cells. So these three cells are I type. There's other I type cells here as well. I didn't complete the entire expression, but I got you started off with these three cells. So these two are covered by this first expression. If instruction bits 6 down to 3 are 0, 0, 0, 0, we're one of these two cells, right? I've not included bit 2 because bit 2 is the distinction between these two. They're both I. Right, so as long as bits 6 down to 3 are 0, 0, 0, 0, and then for both 0 and 1, it's I type. So I just compare bits 6 down to 3. And then for this cell, I'm comparing with 0, 0, 1, 0, 0. Okay, and then you can add in or this case, that would be I type. And then continue on for the other types, right? So S type, R type, U type, J type, B type. Make sense? We haven't added the decode logic yet. So the So I've seen a lot of folks doing similar things, so let me just address that with the whole class. Many folks are creating an expression, for example, for the instruction that's hooked up to the iMemory data that's specifically considering whether we're in reset or whether the read is valid. In this case, that's the same thing. So, maybe something like if reset, then either provide an explicit zero value or hold on to the value. So some folks are doing something like this. And only grab the data from the memory when we have a valid instruction that we need to read. It's all fine. It's not wrong. It's also not necessary. We're only going to use the instruction bits if we have a valid instruction. So there's separate logic that knows if our instruction is valid and is deciding whether to operate on it or not. We can allow the instruction to be whatever in the cycles that are invalid. And that's kind of consistently the methodology that we would use. You'll have control logic that needs to know whether you're doing something meaningful. You use that control logic to gate things like update of microarchitectural state. But the actual computation that's performed in the transaction, so basically the microarchitecture tends to be composed of the transactions and the logic that's acting on the transactions and the microarchitectural state that's updated by those transactions. So the transaction marches along through the machinery. In our case, it's a simple pipeline. It's going to be a simple pipeline. We fetch the instruction. That's our transaction. It's going to march through the CPU pipeline. And as it marches along, it's going to update microarchitectural state, things like the register values or writes to memory. Those where you have microarchitectural state that carries over from one instruction to the next instruction, that's where you need to make sure that you're not updating that state for invalid instructions. But we will tend to cut off things at that point, at the state. And the transaction itself that's marching through the machine, in our case the instruction, if it's not valid, it can be whatever, right? And so that means we don't have to have all these special conditions for if I'm in reset, if the instruction is valid for much of our logic. We'll only do those kinds of things where we update microarchitectural state. So that's why I just have it directly connected. I only care about the case that's valid. Don't have to worry about the others. There's no reason to, hold on to the previous instruction. It just needs to go down the pipeline once. We're done with it, and it doesn't matter. So just something I saw a lot of folks doing. So just to kind of clarify the thought process that we're following with when do you need to reset, when do you not, when do you care about the data, when do you not. I'll work on my code as you guys finish up yours. Yeah, you can thank Google for that one. Thank you. That would have gotten me. So yeah, for everybody else, if you're copying from the slide, this tick is going to be the wrong tick. Let me see if I can fix that in the slide. Yeah. Synchronous. To see what? So it will exist in the generated code. So the question is there a way to see the memory contents? So if you look in NavTLV, right, that's got all the macro expansion that has constructed the memory to contain the right contents. So I'm searching for instruction. Actually, so you do see up here, there's no actual code here, but just comments that are generated as you assemble your code. So you can see these. Then actual memory. Okay, the actual memory is all glommed into one line here. So you'll see this is, there's an instruction array. This is using Verilog. And we're assigning the contents of that whole array. So this first expression is entry 0. So the assembler has decoded the instruction and figured out what are all the bit patterns and generated this string for us to represent that. Yeah, this is going to be 32 bits. So the visualization at the moment does not have anything that specifically reflects the instruction type signals. So there's nothing to give you a hint in the visualization that you got it right. Try to get it right, move on. You might stumble over issues in later labs and have to come back. That's going to be the nature of the work. When you run into bugs, fix them at the time. And we're ready to move on and use the cards. Go back here. It's working. If you haven't finished, finished debugging that one or typing it out, don't worry. I'm going to jump back to the slides and introduce the next lab. After I introduce the next, I'll show my code again if you're still using it for reference. So continuing with decode, at this point we know what type of instruction we have, so that tells us what the fields are. The first field we're going to look at is the immediate field. We'll do the hard one first. The immediate field is distributed all over the instruction, and it's distributed differently depending on the instruction type. So the approach we'll take here is we're going to define a signal called immediate, which is the immediate value for this instruction. One way or another, that immediate is going to get used. It might be an operand for the arithmetic logic unit. It might be an address to update the PC. However it's used, it's going to be used as a 32-bit quantity. So we want to pack the bits appropriately to fill in that 32-bit immediate field. Yeah, so obviously the instruction itself has fewer than 32 bits. We're feeding into some operation that's going to be a 32-bit operation, whether that's the arithmetic logic unit, where it's providing an operand, right? And the arithmetic logic unit is designed to operate on 32-bit values because it might be operating on register values, or the immediate, seems like we're cutting in and out here, or whether the immediate is an offset for a branch, it's going to be added to a 32-bit value. So either way, we're using it as a 32-bit value. So add it appropriately for the 32-bit operations. And we're going to, regardless of the type, we're going to assign the same signal. So depending on the type, we want to pack the bits differently, right? So anytime you have a bunch of cases, we're going to turn to our ternary expression. As I said, we're going to build this whole CPU out of muxes, basically. So based on the instruction type, you have an expression for packing the bits. So I've started you off with I-type, right? So I-type is up here. If we look at this table, which comes from the RISC-V spec, this is the way the bits are packed. This syntax up here, using instruction bit 31, is indicating that instruction bit 31 is replicated. This is actually doing a sign extension of the number. For sign extension, you take the upper bit and you replicate that. So this is a replication of bit 31. The lower bits here are broken into fields that kind of match the way the fields are broken up in the instruction normally, but if you look at these bits, they're actually contiguous. I don't know why they decided to represent it this way. But this is just instruction bit 30 down to 20. So to form that in the code, we need 21 bits of instruction bit 30. That covers these, concatenated with instruction bits 30 down to 20. Right, so remember our concatenation operator is the squiggly brace with commas, and our replication operator is this really ugly squiggly brace, number of replicas, squiggly brace. So this is our 31 copies of instruction bit 31. Okay, so this is for I, and then you'll continue that expression for the other types. Make sense? So I've entered the solution here. When we come back after lunch, starting at 2:30, I'll continue on with the next lab. So if you're not quite done with this, maybe come back with enough time to finish it up before 2:30. Okay, feel free to head to lunch.